Thank you for the introduction. This talk will be about hardware cryptography, and actually I've split it into two parts. So the first will be hardware for cryptography. We try to build some hardware which accelerates certain building blocks in some protocols. And then in the second part, I will try to talk about cryptography for hardware. We have some hardware, and maybe how can we rearrange stuff in the protocol such that it runs faster on the hardware. All right, so let's start. First part, hardware for cryptography. So how does the landscape look like? We have a lot of modern protocols, modern cryptographic protocols. This talk will be mainly about zero knowledge, but we know there's also like fully homomorphic encryption. There's MPC and like a lot of combinations between those two recently, also in the machine learning area. And what we know, or what we, in the last couple of years, what we know, of course, is that this field moves very fast. So arguably faster in some areas than in others, but overall we can say it moves pretty quickly. And that's the reason also why in all those protocols and the changes and so on, the huge focus initially is always software. Why is this the case? Well, of course, software is very easy to adapt. It's very easy to extend. And arguably it's also easy to write. Now, of course, it's hard to find a good software developer, but arguably we still have more of those than hardware people. So many people know it, so we have some protocol, and many people from the community can actually start changing building blocks in the protocol and adapting things, especially during the design phase. So the thing is, though, that cryptography is not only about security. Maybe it was only about security like a long time ago. Nowadays, we know how to make most things secure. So it's not the main point anymore. The main point nowadays is, of course, we want to have speed while still maintaining the security. So that's maybe the thing about cryptography today. And it's about speed here, about optimizing things, about making them faster than they have been in the past. And the thing about speed is that it's very, very hard to beat a good hardware implementation in terms of speed. So if we compare a software implementation of some protocol and then we design a custom hardware which does this protocol, then, well, in many cases, with some caveats, the hardware implementation will be a lot better, a lot faster. And now I'm not talking about a specific piece of hardware. This can be a GPU. We consider this also hardware acceleration, right? It can also be an FPGA, an ASIC, so all things hardware which are not a normal CPU. But of course, if we compare this now to the software approach before, which we used to like build new protocols or like design new protocols, we have a very different set of properties here. So for example, it's very hard to adapt an existing piece of hardware. It's very hard to extend it. It's hard to rewrite it, especially if you think about an ASIC. If the ASIC doesn't work because some instructions do not work, it's not so easy to rewrite those. And also, there are few people available to do it. So for many pieces of custom hardware, for example, there's a certain set of tools you can use to write it. Sometimes it's a custom set of tools or custom tools, and people don't really, so it's not open to the public. There are some exceptions like CUDA and so on, but for ASICs especially, that's the case. And also this doesn't apply to GPUs maybe, but to custom chips, there's potentially a much larger initial investment which needs to be done in order to like print the actual chip if you want to do it. So, well, it makes sense then, of course, that a hardware implementation is not the preferred choice if we are in the experimental phase of some protocol design. So what is this experimental phase? And I don't actually like this snarks and starks distinction because one is, well, arguably part of the other, right? The same in some cases. So, but still people usually know what's meant. So there's snarks, there's starks. There's univariate provers initially, a lot of multivariate provers also recently. There are a lot of different prime sizes. We started those, like we've heard before, with binary fields, then we moved to prime fields again. Now we are at the binary fields again for some protocols. So a lot of different prime sizes, a lot of different characteristics in the fields. We have these concepts of recursive provers or folding. So we have many different components which make up the current stack of the CK protocol design. But between those components, there are also many similarities. So it's not that if we build a hardware, we build it just for one protocol and it doesn't work for the other protocol. Usually we can exploit some of the similarities between those components. yeah, that's one thing. And the other thing is that some building blocks nowadays start to get like standard or become standard choices. For example, there's, of course, everyone knows Plonky 2 or Plonky 3 is very important in the area right now, but also other building blocks which become more or less standard, so we can focus on them. So yeah, as a conclusion of this slide here, we can say that the area has become or is becoming much more stable than it has been many years ago. This may change, of course, may change again, but right now we have some standard choices, which is also related to the fact that we put more confidence maybe on some building blocks now than 5 years ago. So yeah, what does this mean? It means that we can actually start implementing some custom hardware, right? Because we're not in the phase anymore where everything changes every month. So maybe we can think about accelerating some building blocks which have become, for example, default standard choices or per se standard choices. So yeah, let me just put this here. This is actually a picture from Fabric's VPU. So this is a single chip. And does this probably not work, right? Is this a red button here? So, yeah, but it's not working on the screen's too bright for us. I figured, yeah. So, but still, we have those tiles. We have 40 of them. Each tile is a core. It's essentially a very small processing unit with a set of instructions, with an SRAM, which is per core essentially. Then we have those memory arrays. We have here is the connector. We have some RISC-V also there. So this is one chip. And on one card, so to say, for acceleration, we have 3 of those chips. And just interesting to see that this is very different than a normal CPU. So yeah, just putting it out there. So how does it look like, the hardware? Well, we have, or what can we do on a hardware like this chip, right? What we can do is we can have, for example, a very custom instruction set. We can think about which operations do we actually need in a ZK protocol. Do we need a lot of ring additions or integer ring multiplications? Maybe not. Maybe we don't need many of those. Maybe we need more finite field multiplications, actually. So we can think about adding native arithmetic in finite fields. And this includes all these things like reductions and all of that. So that's one thing, native arithmetic. We can also think about very special instructions. So if you know, in many of those provers, we actually need NTT operations, many of those. And one core component of the entities is butterfly operations. This is a version of the CUDA toolkit. The twiddle factor is missing, but still. So we have an instructions, for example, which does both of those calculations at the same time, which is not really possible in the CPU. And other special instructions, like some linear layer computations for hash functions, for popular choices for that, and so on. And what we also have, just looking at this picture here, we have a lot of cores. We multiply this by 3 because we have 3 chips by card and so on. And every core has a certain number of lanes for the computation. So we have a huge potential for parallelization on hardware, which is also not true for many of the normal CPUs. Of course, the changes for GPUs, they're also highly parallelizable, but still. So this results in a lot of computational power. We have a lot of compute units, native instructions, and so on. But something I want to focus on also in the later part of the talk is maybe this, in some cases, this doesn't actually give an advantage because we're limited by the memory. This is also something sometimes we forget it, but then it doesn't come as a surprise that the memory is, in some cases, much more important than the compute units. And specifically for this chip, for example, we have some connections, of course, between all the cores. This is called a network and chip, a NOC. And we have to think about how do we get one piece of data from the memory component in the top right to some core on the bottom left, for example. So there's some latency and some delay involved, and this is all memory related, not compute related. All right, so this is a very high-level overview of the hardware we can do for cryptography. There's a lot more than that, of course. So I'm not going into all the details. But the other perspective or the other direction we can try to make here is if we have some hardware, how can we actually, or if we know what the hardware can do, what a piece of hardware can do, how can we change specific parts of existing protocols in order to run faster on specific types of hardware. And yeah, I'm just giving some examples here, and some of those are not finished, but still. So the first thing we can do is we can think about prime field choices. This is, of course, a very important thing in all these CKVMs and provers because it changes a lot of the characteristics of the prover, right? So what are the prime fields? And we've already heard about that before a bit. So initially, we started with very big prime fields. So this is true for KZG, for example, for these elliptic curve-based provers, but it was also true for the Starks today. We started with big prime fields, and then we got like a bit smaller to 64 bits. That's a Goldilocks prime, actually. And then we went to 31 bits, which is like, for example, Baby Bear or Mersenne 31 and some others. I forget the names. Or even 1 bit. In Binius, for example, we even go to 1 bit and extensions of that. But yeah, so field sizes have been shrinking, and what's the reason for that? Well, of course, with smaller prime fields or smaller fields in general, we have a lot of advantages in software, because for the computations, we don't need as many limps. We have, this leads to fewer instructions. We have easier representations in AVX, for example, and so on. So smaller prime fields are actually nice. So the question is, do we actually lose something by going to the smaller prime fields? And we'll also talk about this in a minute. So in a hardware, the situation is similar, of course. We have more efficient wiring if the computations are smaller, but we have slightly fewer restrictions here. So we can think about, for example, slightly larger prime fields. Also going to talk about this here. So, okay, and I'm here focusing on a univariate prover, on a very classical univariate prover, like what SB1 has. I think they also have a multivariate version now, but what SB1 has been doing, for example. And in these univariate provers, we know some properties have to be fulfilled. For example, we need to have a fast entity for part of the commitment, for the extensions also. And now, if we ignore stuff like M31 and so on, we need a prime field which allows for high two-adacity in order to have a large enough group where we can do actually the FFT. So this has to be fulfilled. Also, the arithmetic has to be efficient. The reduction has to be efficient. So we cannot really choose any prime. We have to, for example, take care of the coefficients in the powers of 2 representation. This is for faster arithmetic. And then we can also think about something like a low degree map for the prime. So essentially, it's not so important here, but it means that we can use some hashes for recursion better because we can use a lower degree constraint for those. And finally, we need something like a low embedding overhead. And that's now the reason I come back to that. These huge primes, and I think we already heard about it before also today. If we commit only to 8 bits, but we use a 256 prime for that, then we essentially lose 248 bits, which is not really good. So the lower we go, the less we lose, so to say, in terms of real-world use cases. All right, and the scenario I'm considering here, just to give the example, is the arithmetization of some ZKVM. So what we usually want to do is we want to prove some instructions. Let's focus on the RISC-V one over 32-bit integers. And of course, we can now think about, okay, which prime field do we have? Let's assume we have this 31-bit one, right? Mersenne 31 or the Baby Bear one. Then we can immediately see that we cannot fit a 32-bit integer into a 31-bit prime field element. So this doesn't work, and we need to split the inputs essentially into limps. Okay, so let's try 16-bit limps because it's a nice number. We are fine for the addition because at most we have the intermediate result being 17 bits, which still fits inside the prime field. But then if we think about the multiplication, of course, it doesn't work anymore because the intermediate result is at most 32 bits again, and we cannot really fit a 32-bit element into the 31-bit prime field. So yeah, this doesn't work, and we need essentially to move to 8-bit limps. And this is, by the way, a very stupid trick. It's not really interesting from a math perspective, but still, just to show you what hardware can do here. So we need to move to 8-bit limps, which means we have a higher embedding overhead because we essentially are wasting 75% of the prime field size only to commit to the 8 bits here. And in some provers, this also means that we need a lot more entities, and entities or FFTs are one of the bottlenecks in the provers many times, at least when not accelerated. Okay, so the result, so the solution is very easy, right? We just switch to a larger prime or to a slightly larger prime here. But well, it turns out not to be very efficient on software, and that's the reason we moved away from those, because we don't want to have those large primes. It turns out, though, that on hardware the situation is of course different, because we can try to use some primes which are, for example, 33 bits large, which is really bad on software because 33 bits you always go out of the bounds of the word size, right? It's really not so good. But on hardware, it's not a big problem. You can just like additional wiring, and it's fine. You can still do it very efficiently in a native way. Of course, the memory is the same for both, right? It's usually byte-aligned, but there are some techniques which are very similar to bit slicing in cryptography, which can also be applied to the memory. So we are fine also for the memory. What would this mean? Well, we move to larger primes. We can store the 16-bit limbs instead of the 8-bit limbs like before. And yeah, just to give an example for such a prime, so I call it Panda Bear, but it's very easy to find one. There are also better ones than this. But yeah, there's 33 bits. It has a high two-adacity. It allows for efficient recursion because we can use this low-degree power map, which we use in some hashes. And it has also a low Hamming weight, so we can do fast reduction, even though arguably we don't really need this on hardware, but still it's much better also on hardware. So what's the actual advantage then? And we just compare it. This is a circuit. I believe this test is from SB1, but I'm not 100% sure anymore. Yeah, so the setup is 2 to the 18 times 16 in 32 multiplications. Then, for example, if we use Baby Bear, we are kind of forced to use 8-bit limbs, and we need 256 columns. For Panda Bear, for this new prime, we can use 16-bit limbs. We approximately half the number of columns, and very surprisingly, we also approximately half the number of LDE operations here. Yeah. So yeah, that's a significant reduction in proving time. Of course, it's not like 50 or 44%. It's more like 20% or something. Depends on the bottlenecks, of course. But still, we have a reduction in proving time. We have less wasted space, and the advantage also translates to additional steps like the Merkle hashing and so on. So this is one thing we can really not do on software very efficiently, but on hardware, it's not a big problem to do this, for example. All right, so that's about memory usage. Very quickly, also wanted to talk about the access patterns. This is more interesting maybe when you try to actually implement some proving system, or when you think about an implementation on custom hardware. But it also makes sense on the CPU to think about that. So usually what we need in those proofs is that the prover needs to store all the evaluations so the post-LD evaluations. There are some ways to mitigate this, to like discard them, which requires some additional techniques. I'm not going to go over these now. But this usually means that we have a large memory footprint. So this is many of gigabytes. And many of gigabytes, like 8 gigabytes, is not so bad if we consider CPU, right? But if we consider custom hardware, then 8 gigabytes may actually be a lot already. So the limitations are also different, not only the capabilities. All right, so for example, we need to think about what can we do with the LD evaluations. And one thing we're currently doing, and just to give a quick example here, so this is how it's usually done. We first do the entities, all the entities, so which are the low degree evaluations, right? And then we do the hashing. In some of the modern protocols, though, the hashing is done over the rows and then over the columns, and the entities is done over the columns exclusively. The problem for that is that if we have a large number of, a huge size for the columns, and usually we have like 2 to the 20 or even higher, then in order to do this efficiently, we have to have the memory right beside each other for the LDEs, which means that we store this or want to store this in some kind of column major order. But then we go to the hashing, and we need the hashing to essentially do the transposition of that from the memory access perspective, which means that for the hashing, it would be better to have the data in row major order, which is a problem because we need to convert it. And it turns out there are some ways to do the LDEs and just write back into the right order, so we can do the hashing immediately in the right order, and we don't lose time on the memory side. But all of these things are very important when we think about how to implement something on hardware. And yeah, another thing is, and this is also true for many components, that if we accelerate both the entity and the hashing, then in many cases the entity is memory bound, which means that we need to fetch and write and read a lot more data than actually we need to compute it. Computations are not so expensive, but it's the other way around for the hashing. Usually the hashing is not memory bound, but compute bound, because we have a lot more computations than data access, actually. So if we start doing the LDEs, and after the first batch of LDEs, we already start doing the hashing, while we are still doing LDEs, or while we continue doing LDEs, we can try to merge, for example, the memory bound part with the compute bound part. Of course, this requires a lot of adaptations also on the hardware side, but these are some optimizations we can think about here. Okay, so finally, I also want to talk about hardware-focused symmetric primitives, one of my favorite topics here. Yeah, in all those provers, for example, the Merkle tree hashing is often a very crucial component in terms of bottleneck. If you don't accelerate it, it's a problem, right? And the thing is that popular prime field primitives, like for example rescue, they're not really hardware friendly. They have lots of prime field arithmetic. We need a lot of native instructions for those, and the CPU doesn't really support it. We can build a hardware that supports it, of course, but then we need to include this instruction. And yeah, recently, of course, with the rise of these binary extension fields, also for efficient proving, we also have different primitives like Vision Mark 32, which focus on binary extension field hashes, for example, also on hardware. And just to give an example that this is more like a side effect than the aim or the goal of this primitive. So monolith is also one of the recent hashes which are optimized for prime field provers. And inside monolith we have this function which is called bars essentially. It's part of the round function. And this is not using native prime field arithmetic. Instead it's using simple like shifts and XORs and ANDs and one negation here. So it's very similar to what we actually used to in the classical hash functions like SHA and so on. And yeah, how does the proving work if we don't use native computations? We just use the lookup arguments, and turns out it's quite efficient. Well, it brings other disadvantages for the provers like a huge witness size, but for the computation, native computation alone, that's very efficient, and also on hardware, it's very efficient. All right, another thing, that's the last thing I wanted to talk about when we think about hardware and what we can do is we can try to reuse some of the components. Specifically in the LDE and the Merkle hashing way, right? We have first the LDE and then we have the Merkle hashing, and we have different instructions. We have this A plus B, A minus B for the LDE. We have different instructions potentially for the hashing, so we need to kind of accelerate them both with different instructions. But what we can do, of course, we can think about a very simple set of instructions which accelerates both of these steps, which often are actually both of the bottlenecks of the proof. And yeah, these ideas are not very new. So for example, it has been done for Swift. It's another hash function which is like reusing components of the FFT, but in a very different scenario, so to say. So what are good candidates? And just to give an example, on the left we see a butterfly computation. This is a Cooley-Tukey butterfly. So the ID is just the identity function. And on the right side we see a Banach network. A Banach network is not really a Feistel network, but it's a kind of a Feistel network, very similar to it at least. And it can be used to build a symmetric primitive, like a hash function, and even an algebraically friendly hash function here. And we see immediately that those two components are essentially the same. If we choose the F function such that it matches those, then we have the same component. So the idea is, if we can build this on hardware using a set of instructions, then we can use the same area on the hardware essentially to accelerate both the LDEs and also the hashing. Of course, there's other things we need to take care of. For example, how do we actually choose these F functions, both for cryptanalysis, for efficiency, but also for invertibility. This is a different topic. But the point is it's possible to define such a function which is very similar to the butterfly operation, and we can use it also to do the hashing with that. And the nice side effect is that the linear layer is not really needed anymore in this case, and we save a lot of native computation time here. The linear layer is usually a component in the hash function where you lose a lot of time because you do, for example, some matrix multiplications, which are time intensive. All right, so that's already my last slide. Seems I rushed it a bit. So what's the future of hardware? Of course, besides CK, there are a lot of other use cases, right? For example, FHE. And it turns out, if you take a look at these use cases, that some of those, for example, CKKS, are very similar in terms of storage structure. You also have, for example, this matrix way of thinking. If you have these like composite representations with different polynomials, you can think about a matrix structure or storage structure which is very similar to that of CK. So you can use a hardware which is optimized for CK in a way also to do things like CKKS. And why is this maybe important? Well, there are some use cases recently, for example, this all machine learning stuff where you send your input and you want to send it in a private way and to get it mixed in a private way with the model, and then you can use something like FHE for that. It's the discussions about efficiency are for somewhere else, but this is one of the use cases. Yeah, sometimes we have though different characteristics, like the primes are different. In particular, for these use cases in FHE, we usually use many different primes rather than just like Baby Bear or M31. But what's also important is if we build some hardware, we should try to keep it general. So it can actually also support those use cases or other protocols in ZK, at least as much as possible. If we make it very general, we end up with a CPU or something like that. So that's not possible, of course. But we need to try to not make it too specific. And one other thing, this is something that's also very important for the future, is that we need some easy access for programmability. So if you just think about CUDA for NVIDIA GPUs, like you can learn CUDA, you can accelerate something using CUDA on your GPU, and many people know how to do CUDA. But on hardware, it's really not really known. You get a chip, but how do you program it? So this is part of the reason that hardware isn't used, at least so far. Yeah, and finally, a lot of things can be done for co-design between cryptography and hardware. This is very hard because, of course, we need hardware which is easy to program, such that we can experiment in the design phase of protocol. But if we actually build a protocol with the goal of running it on hardware instead of CPUs, then I think we can find new advantages and new performances here. All right, thanks a lot.